For next couple of slides, we'll learn about sedimentation. So how to remove suspended or non-suspended sediments or total sediments in a stormwater retention ponds. Again, sedimentation means you have larger or heavier particles settle at the bottoms faster than the lighters or smaller particles. Here is a picture of sediment tank. So here stormwater comes from this side, and then you can think that by the time it exits from the system on the other side, it is going to settle. Well, in this case, this is not overflowing, so that means most of the particulates will stay inside the system. So there are equations that describe the sedimentation velocity, which you learn in the CEE159, but I'll just give you a brief description here. Again, think of this is a particulate. It has a density of particles, and it has a size, which is dp, with the diameter of the particulates. So anytime you have a particles in water, it has always a gravitational pull to push it down. So that's the downward force. As it moves downward, it has there are two other force act on it. Number one is the drag force, which is related to frictions, and that's here. And then also there is a buoyancy, because it displaces a certain amount of water. The weight of that displaced water is the buoyancy force. So that means based on Stokes' law, when the particles moves at this constant velocity, that means there is no force act on it, because force is mass times accelerations. Acceleration is 0. When force is 0, acceleration is rate of change of velocity over time, 0. That means velocity is constant. And that's called velocity of settling velocity. And you can determine by balancing those two forces. That's why written here. The left side you have a drag force, and the first one is gravitational pull, and the second one is the buoyancy force. When you know that this is the settling velocity. If you rearrange the equation, you determine the settling velocity as a function of particle size, that's square, difference in their density, because the denser is the particles, it's going to settle faster. Then gravitational g, g is the acceleration due to gravity, which is 9.8 meter per second square. And then you have viscosity of stormwater. Again, if you have viscous stormwater, it will take longer to settle. So that's why if you increase viscosity, it decreases settling velocity. You'll use this equation to calculate the settling velocity and the percentage removal. But again, settling velocity tells how quickly things move downward. The idea of removal means the particles must settle before it has the time to exit the system. So that means it is related to how quickly particles or water is getting out of the systems. That's we call overflow rate. Overflow rate means, think of this as a detention pond. If flow is coming in, all the stormwater that overflowing the system is moving upward, right? So that overflow rate or the velocity is, if you know this area, that will be flow rate divided by area is the overflow rates or velocity of overflow. So that means if your particles are settling faster than overflow rate, that means most of the particles are going to be removed. So if V0 is greater than equal to velocity of settling, all particles removed. If V0 is, I'm sorry, this is, I wrote it wrong way. If overflow, if the settling velocity is more than, yes, you are right. I'm sorry, what I'm thinking. This is if V0 overflow rate it's flowing much faster than the settling velocity, then only the fraction of particles that's related to that will be removed. So that means removal would be velocity of settling by V0. If V0 is less than equal to velocity, all particles are removed. So this is what you need. You need these equations to calculate the percentage of particles are removed by the systems. So these two equations you can use to quantify the amount of particles removed. So this is first examples. So this example said determine percentage of suspended sediment with size 10 micrometers and specific gravity 144 would be removed by detention pond, receiving stormwater at a rate of 7,500 meter cube per day. Viscosity is given. All right, so viscosity is given 0.001002 kilograms per meter second. Your flow rate is given. Stormwater flow rate is given, which is 7,500 meter cube per day. You can calculate in terms of meter cube per second because you have a second here. So that will be 7,500 meter cube. And 1 day is 24 hours. It's 24 times 60, that's in minute, in second. So you got this flow rate in meter cube per second. Then you have to also calculate, it says the percentage of sediment particles. So that means you have to calculate removal rate, which is settling velocity divided by overflow rate. And settling velocity, you know, by Stokes' law, which is density of particles minus density of water times d square. Then it will be 18g. So that would be the way we can calculate the value of this divided by velocity of that divided by velocity of overflow rate. So that will be Q over area. So Q is given. Area is the top surface of the area. So that's 30, 10, and 1. So that will be 30 times 10 would be 300 meter square. So you know Q, you know everything else. So let's say specific gravity is given. Specific gravity means the ratio of particle densities. So that means this by or is given 1.4. So that means you can say that the particle is 1.4 times heavier than the water. Water density is if you write in terms of kilogram, so it will be 1,000 kilogram per liter. So that is let's say it's I'm sorry, not liter, meter cube. So that's 1 kg per liters. All right, so let's, you know all these numbers, so that means you can calculate this will be 1.4 times 1,000 kg per meter cube. So that will be 1,400 kg per meter cube. So if you put it here, everything is given, 14,000 minus 1,000 kg per meter cube. Particle size, D is given to, D is here. The particle size is 10 microns, so 10 times 10 to the minus 6 meter. So that's 10 to the minus 5, so 10 to the minus 5 square times meter square times G. G would be acceleration due to gravity, 9.8 meter per second square, divided by 18 times mu. Mu is 0.001002 kg per meter per second. Then you have then from this one you can calculate area will be on the top side, so that will be 300 meter square divided by flow rate. Flow rate is, you have equation here, whatever that number, so that will be here, meter cube per second. So you have everything meter, kg cancel out. All the meter, you'll everything else will cancel out, so you'll get the percentage. So this will get a number, fraction number. If you want to calculate percentage, you multiply 100. All right, so again, it's all finding what terms are given, changing the units to same unit so that you can calculate the numbers. The second one is about calculating the minimum size that can be removed by detention pond. Again, you are saying that everything will be removed. So that means you can equate overflow rate, which is VO, should be equal to velocity of settling. That means everything will be removed. And then you can say what's the minimum size of particles required for that to happen. Because anything above, particle size will settle anyway. So if you solve for this one, you get these answers. And so you can apply that to solve problems. Again, example is here, determine the smallest size of suspended sediment with specific gravity 1.4 that would be completely removed in the retention part, the same one that we discussed before. It's all about writing the equations. So dP would be Q over A times 18 mu particles mine. Well, okay, type half. You know flow rates, you know area, everything else is given. You know acceleration due to gravity, as water density, as well as particle density. Just plug the number, you will get that answers. So there is nothing else really to solve. All right, so that's the end of sedimentation. So hopefully you learn how to design the system so that you can remove particulates, suspended particulates or sediments from a systems using Stokes law.